Well, good morning, ladies and gentlemen. First of all, I would like to thank the Thierry and the organisers for inviting me to come to give this talk this morning, which is a great pleasure, and also to thank Thierry personally for the help that he has given me, and also, I think, to thank all of these young people who've been doing such a grand job, and I think we're all indebted to them for that. Well, I suppose that you can see the title is probably means that you can see there is going to be something different, and I suppose this title should be "And Now to Something Different." However, you will see links with what's been going on in the previous talks in the week, except that I don't think I mentioned Sobol, which perhaps is the first paper that hasn't mentioned Sobol. But you'll see why. Now, I'm going to talk about an approach to modelling called data-based mechanistic modelling, and I'm going to apply it to a climate example, and in particular to the forecasting of global atmospheric temperature. So let's look at the background to the methodological approach. There's a philosophical element to this, which I think I should stress because someone brought it up previously, and I think it's very important. The 20th century was marked by a particular approach to science that was extraordinarily successful and was perhaps mapped out best by Karl Popper in his treatise on the scientific method. And he termed this approach the hypothetico-deductive approach. It's interesting, if you look at Popper's book, that the word experiment appears hundreds of times. And the whole point is his methodological approach was for looking at data from planned experiments. Now, I've been involved for at least half of my life in the environmental sciences and macroeconomics, where you certainly can't plan experiments. Perhaps one or two in environmental science, I don't think, unless Mrs. Thatcher in Britain was an experiment, I don't know, and perhaps Brexit's an experiment, you never know. But you can't plan the experiments, you're confronted by data that you measure. Now, for that reason, I don't think that Popper's method theory, if you like, necessarily applies very well to data like that. Yet it's being applied to data like that. The climate model that I'll be talking about is one of the biggest models ever built. At one time it was taking 2 weeks on a supercomputer to run one run. So they have built meta models, smaller models, but they're still very large. And they're all based on the hypotheses put forward by climate scientists. Now, they're very clever people, climate scientists. I don't think anything I say is being extra specially critical of them. I will be a little bit critical, but not extra specially. But I don't think that they realize the problems of modeling from data that isn't from planned experiments. And the fact that there can be not sufficient information in the data they have to build their models. The opposite approach is inductive approach. And this is the approach used by most people who are dealing with the modeling from data. Of course, you can't separate these two. The inductive approach is actually much older and was the approach used in the time of the scientists of the 18th and 19th centuries who were not making hypotheses. In fact, Newton says, hypotheses non fingo. I don't appreciate hypotheses. They're not what I'm about. Because he was looking at data and trying to infer from those data laws of nature. And he was very successful in doing that. But I don't think you can split these two. So the data-based mechanistic approach is one that tries to blend these approaches. Now, this problem with this hypothetico-deductive approach is it leads to these large models. And I think anybody who's looked at large models and tried to fit them to data will realize that it's impossible. It's impossible because the amount of information in the data is insufficient to estimate the parameters because there are so many in the model. So people get round this in various ways. The Bayesian approach, for example, if I have time, I'll go into my criticism of the Bayesian approach, because it all depends on the priors. And if you make the priors tight enough, you'll converge. But are you converging on the right answer? That's another question. So one thing that you can do with the large models is meta-modeling, or as I'll call it, emulation. And so I'll be talking about the emulation of a climate model. Actually, I'm talking about the emulation of a climate model emulator. That emulator is very large. You'll see my model is very small in terms of dynamic order. And that's another thing that I should stress, is the DBM approach is intended for dynamic systems. A lot of the examples this week have been static systems. This is dynamic systems described by differential equations or their equivalent difference equations. Now, database mechanistic modeling is quite simple. Really, I put it here as two things. First of all, you use induction, you analyze the data, and we've got some very powerful methods now for estimating models against data. And you'll see the results of some of those. That would be standard. Econometricians estimate economic models from data. Lots of engineers, scientists estimate models, but quite often they're black box models in engineering anyway. The whole point about the DBM approach is that you're not finished when you've fitted the model to the data. You have to make that model credible. The model has to be credible to the discipline that you're talking about. So in this case, my model should be credible to a climate scientist. I'm not sure it still is, but you'll see what I mean. And if you're modeling in this way, there is a distinct advantage for modeling in continuous time. That is, using differential equations. Now, strangely enough, the estimation of models for continuous time models is a thing that hasn't received a lot of attention. In fact, if you look in the time series statistical literature, the only ones you'll find are stochastic differential equations. And you don't need stochastic differential equations to fit differential equations to data, as you'll see. Right, so let's move on. Emulation modeling. Now, there are various ways of building a small model that behaves like a large model. And I'm not going to talk about all of those. I'm going to talk about the DBM approach to emulation, which is rather different to other approaches. Now, you'll see that this DBM approach can involve sensitivity analysis. I won't be doing that for this example that I'm looking at, but it can involve that, and I'll point out how it can involve that. An important aspect of the DBM emulation is that it does look at sensitivity, but it doesn't look at the sensitivity of the output to the parameters. It looks at the sensitivity of the output to the dynamic modes of behavior. Okay? Now, I'll explain what the dynamic modes are if you're not aware of that. But these modes, we find there are certain dominant modes. And these dominant modes are few, but not many of them, and they dominate the response of the system. And if you can model the dominant modes, you can model the system with a very low-order model, almost exactly, which is surprising, but is nonetheless the case. Okay, now emulation modeling in this case is shown in this diagram. If I can find where the red, doesn't seem to be working. Can anybody see a red dot? You can see it? Well, more than I can't see it, but anyway, at the top, we have a high order model on the left. Oh, there it is. Yes, that's that one. Yeah? Oh, yes, there we are. Not very easy to see from here. I have to come down there. Yeah, as far as Where's this? Oh, there we are, there we are. Got my finger in the right place. As the art mistress said to the gardener. So here on the left, oh, can't get this to work. Anyway, on the left is the high-order model.
Yeah. You just say left, right.
Yes. So on the left is the high-order model. And this could be very big. On the right is the low-order model. That's where I want to get. And at the top, you can see the high-order model and the low-order model with the same input. So I'm going to put inputs into this model and see what the output does. And now I'm going to analyze the input-output data to find the model. Now, nominal emulation is when I find a low-order model that represents the high-order model for the parameters that are set. So just a single set of parameters. Now, if I want to have a complete emulation model, I have to do the lower block. That is, to map the high-order model parameters to the low-order model parameters. And this mapping is very similar to the sort of analysis that you've all been talking about this week. Okay, so I'm not going to talk about what that mapping is. It can be any mapping you like, but it is a complex hyperspace, hypersurface that you're trying to fit between these two. But I'm going to talk about the top approach anyway. I'll have a go now, save you standing there. Now, I'm going to work with transfer functions. Can you put your hand up if you know what a transfer function is? Okay, well, certainly quite a few. Think of a differential equation. I think you all know what a differential equation is. Well, the transfer function is the operator version of a differential equation, and you'll see it in simple terms later. Now, a man called Liao, quite a long time ago, 1986, and Davidson before in 1966, showed that if you've got a transfer function, you could generate what Liao called, through dispersion analysis, a mapping of the modes to the output. And you could then look, and he could arrange these, a bit like principal component analysis. You could arrange them, and you could find which of those modes were affecting primarily the output. So it's a form of sensitivity analysis, not just the form that's been talked about mainly this week. And the modes that come out as the most influential we'll call the dominant modes. However, I don't use Liao's analysis. I'll point out what I use later on. Now, here I've got at the top, oh, there it is, a differential equation. It's a multi-order differential equation. Can you all see that? And are you acquainted? I'm sure you're acquainted with that sort of a differential equation. It relates the changes in x to the changes in u. And I'm just looking at a single input, single output, but this generalizes. So if I now introduce the operator s for d by dt, and then powers of s would be the first and higher order differential coefficients, I can operate on the right and left-hand sides, and I'll get polynomials in s. And if I then divide the right-hand side by the left-hand side polynomial, I get a ratio of two polynomials in the derivative operator. That's the transfer function. And what Liao showed was that you could expand this in a finite series by by partial fraction expansion. So in other words, he showed that that transfer function could be represented as a sum, a finite sum, of first-order transfer functions or second-order transfer functions. Pm there is the eigenvalue associated with a mode, a dynamic mode of behavior. And it can be a complex number. And when it's a complex number, the system is oscillatory. When it's a real number, the system is non-oscillatory. So what you see is that any transfer function for a linear system can be represented as a sum of these modes. And only a few of them matter, because all the rest don't do anything, or they do very little. So the idea is to find those dominant modes. But the DBM approach goes further. it recognized early on that when you do this, some of these modes can be combined together to form another mode, just a single mode, which represents more than one mode. So, and when you do that, you find you get even less modes necessary. So here's an example. This is actually an example of an emulation model for a climate model. And this was, you'll see it come out in the analysis later on. Now, here is the transfer function. It's second order. It's got a second order polynomial at the top and one at the bottom. Here's the partial fraction expansion. And you can see it's got two terms and a constant term. The constant term is the instantaneous effect. So this says that the input, which here is the radiative forcing, the total amount of radiation-induced heating of the atmosphere. And the climate scientists have a globally average measure of this, and I'll be using that. And the output is the globally averaged atmospheric temperature. See, everything is averaged to the globe. You might question that, and I know Andrea has questioned it to me earlier on in the week, and I would question it, but that's what you've got, that's what they use, we'd better use it. Okay. If we look at this, this can be written in this form by just dividing through by this number. You get 1 plus 20.6, 1 plus 385. This is a nice thing because 20.6 is the time constant of that mode. They're both real modes. And 385 is the time constant of the other mode, 385 years. These are all years. So this is very slow. We know the climate is very slow. And this is the instantaneous effect. So when you increase the radiative force and instantaneously, that's within 1 year, you get an effect on the temperature. Right, let's look at an example, because I think examples tell you about things much better than a lot of maths. You'll see in a minute that you can get to the maths and you can get to computational algorithms quite easily. I'll tell you how. Right, here are the data. Now at the top, by the way, just a general observation. If I could have plotted these on a bigger vertical scale, it would have been better. But they're all going up, do you notice? Except the bottom one. And that's what the climate scientists say. The top is the temperature, and that's global warming. Okay, then below that is the radiative forcing. It's going up as well, and it's the association of that second one with the first, which is what the hypothesis of global warming is all about. Below that is the CO2 in the atmosphere, which is part of the second one. Not the total, because the second one also includes volcanic activity, other gases in the atmosphere, etc. They've all put together, but one component is CO2 in the atmosphere. And you've heard about that, haven't you? Carbon dioxide emissions are causing climate change. And at the bottom is another series, which you'll see comes into play and is not being used by the climate scientists. And that is the Atlantic multidecadal oscillation, which is the oscillation in the sea surface temperatures in the North Atlantic. Now, these models, the climate models that you hear about, are enormous. You cannot believe how big these are. So even the climate modelers realize they're too big to do much with. So they have built a number of emulation models, but the most famous is MAGIC. And the reference is there. But it's 80th order. Right? So that, I know from my experience over a lifetime that 80th order is too high. And I know from these data you are not going to be able to estimate the parameters in an 80th order model from the data you've seen. No way. So I'm going to emulate their emulator. You've got a clue to what it is, because I said earlier the second order model was the model that did it. Okay, now, you may want to do some of this. I hope I might persuade you to do it. And if so, all of the algorithms I'm using are available in this toolbox for MATLAB. Captain Toolbox is free. Just go to website, download it. It works straight away. There's a lot of help in each routine, and there are a lot of demos, so you can use it, I think, people have told me, fairly easily by just downloading it and then looking at the demos and fitting your data into the demos and playing it that way. And also, I published a book, which was published in 2011, Recursive Estimation and Time Series Analysis, which includes the background theory to all of the methodology I'll talk about this morning, and which also refers to the Captain Toolbox and uses it. So, in a sense, it's a technical handbook for the Captain Toolbox, but also a theoretical handbook because it introduces the methodology. And you'll see there's some quite complex and advanced methodology there, which hopefully you would like to read about, but you can use it in Captain anyway. Right, so before proceeding to what is the end product of my talk, I'm going to talk about emulating their model, show you what happens there. I should say, and I should have said earlier, that a model should be related to an objective. The first thing you should do in database mechanistic modeling, by the way, there are at least 10 steps in database mechanistic modeling. You don't always use the 10 steps, and I'm using a few of them here. But the first one is define the objective of the model. And the objective of my model is forecasting the global temperature, because that's what the climate scientists are doing. So here's an experiment. I can do, once I have the model, and I have it in MATLAB, I can do experiments on it. But I put this experiment in because it shows you something visual about the nature of this system. I put a step in radiative forcing, and you can see the dots, the circle dots, are the response to the step. And notice this is 3,500 years. So this is extraordinarily slow. And the second order model is the line. Above it, on a larger scale, is the error. And you can see most of the error occurs at the beginning, but this is only a second order model. It explains 99.7% of the output of the big model. And if I took it to fourth order, I don't, for a reason that you'll see. If I took it to fourth order, I'd explain 99.99% of the output. And not only for this input, for any input that I put in. And the first thing you know, it's a linear model, their model, but this shows that it's linear because the linear model fits so well. And you can see the 20.6 years, the 385 years I mentioned earlier. Now we can break this model down because the transfer functions decompose. And additive transfer functions mean in parallel. So the radiative forcing comes in, and you can see it broken down into an instantaneous effect, a fast effect, and a slow effect. Now, the fast effect, these two together, or the fast, they describe 76% of the effect. And the slow one, only 24%. We can now look at the magic model and see whether this reflects, in some sense, the magic model. And we find that it does reflect the dominant effects in the magic model. And so a lot of is to do with this fast response and less to do with the slow response. Now, at this point, I could build a meta model I could map, but I've not done that now because I'm looking at forecasting, and I don't need to do that, because I'm going to forecast not with their model, but with my model. And you'll see my model is different to the models you've seen so far. So this is from real data. And here's the model from real data. And what? It's a first order model. Okay? It's just got this here, 1. This here is to account for the initial conditions. If anybody knows Laplace transform, this is the effect of the initial conditions, which in Laplace transform, and I used S because S is often used as the derivative operator and also as the Laplace operator, then you'll know that the initial conditions can be accounted for by a term in that. And in this case, there are initial conditions, so I ought to account for them. And I do that. And here's the interesting thing, that the time constant here is a short one. Okay? The time constant on the initial conditions is very long. So there is some evidence of a long mode in these data, some evidence. But it doesn't come out at all in the input-output behavior, only in the initial condition response. And I've never met that before, but it's very interesting. So it's clear that my model, this one, the time constant is 1 over 0.044, which is 25-something years, is accounting for the short term. But then forecasting of a climate system, you'd better forecast in the short term. Because as you'll see, if you forecast in the long term, the uncertainty is so high, you can't really say that you're forecasting very well at all. Okay? And in a stochastic model, this is a differential equation, but it's got a stochastic term. It models the noise. I've seen a lot of things where we have E on the end this week, and it's always thought to be white noise, nicely behaved, normal. I've never met that in practice, I have to say. It's nearly always colored noise. And here, if I use the standard criteria, it gives me this. And the standard criteria are wrong in this case. That isn't a good model of the noise. And you'll see why. There's the fit to the data. And I hope you'd say, well, it isn't very good, is it? All right? It maps the long-term rise, but that's because the input's rising. So it's not surprising the output rises, and there are some jumps in it, and that's due to the volcano effects, which presumably one was here, you know. And if you look at the RT squared is the coefficient of determination based on the simulated deterministic output in relation to the data. So there, you can see that MAGIC is modeling 80%. The model that I've fitted is 85%. So it's better than MAGIC, and it's a first-order model. That's the first point. The second is, it's still not very good, is it? Not good enough for me, anyway. Not good enough to forecast, in my opinion. However, this model has some physical properties. You remember the database mechanistic? You had it be credible. First of all, there's a thing called climate sensitivity. You can work it out from this model, and it comes out to 2.8 degrees centigrade. It's more or less what the effect is over a certain period. And this is in the middle, exactly in the middle of the distribution the climate scientists say. Bounds from 1.78 to 4.25. Why they say 0.78, they might as well say 1.8 to 4.3, you know, because they're never going to get it that accurately anyway. These are uncertain estimates. And so this makes sense. The climate sensitivity of this model is what climate scientists would say is acceptable. The instantaneous response, oh, by the way, it's a continuous time model, and their models are continuous time. Why? Because they're based upon the laws of conservation of energy. And most models, conceptual models, are based on the conservation of something, aren't they? Energy, momentum, whatever. And the instantaneous response, 23.8 years is the time constant, is matching up with that part of the MAGIC model that represents the short term. Okay. So we've captured, but it's different estimate to the MAGIC model. And that's why it fits the data better. because the magic model is not data-based. It's based on somebody's brain. What do you trust better, their brain or the data? It's a stochastic model, so I can look at the uncertainty on the estimates. This is rather nice. This is obtained by Monte Carlo analysis. You're all gifted exponents of Monte Carlo analysis, so I don't have to explain that. Here's the quick residence time. You see, defined reasonably between 20 and 40. The slow, well, could be anything up to 1,000 years. So the slow mode is not being defined very well. And that's reasonable, because the data are from 1850 to the present day. Who's going to estimate anything in the long term from data that only spans that time? And don't the climate scientists realize that? They never mention it. And the climate sensitivity, you can see, again, spans what they say, the uncertainty. So I think you would accept that the model is not bad from a climate science perspective, but it doesn't agree with their analysis. And that's why you cannot get it published in the climate literature. And they say very rude things about you. Very rude things.
You have to increase a bit your climate sensitivity.
That's right, exactly. That's it, yes. Now, here is my model against the data, and above is the error. And that was modeled by standard methods to be a first-order autoregression. And it isn't a first-order, is it? It's obviously not, is it? It's a quite complicated series. But can you see anything in it? Can anybody see something? There's a lot of noise on it, isn't there? But there seems to be a cycle in it, doesn't there? Yeah. It's autocorrelated, and it seems to have a cycle in it. Now, why didn't the climate scientists see that? They never looked at the error. They don't believe in errors. Deterministic models, they know everything. How can you lose? Here is the spectral estimate of that series. And look, the biggest peak, 51.6 years. There is a 50-year cycle in the error. This suggests the model should have something that gives rise to 50 years, and it doesn't, and neither does the magic model, and neither do the climate models. So there's a 50-year cycle in these data, and none of them seem to have recognized it. So what did I do at this time? You can't get to the climate scientists, so you can't go and say, oh, I found this, could you tell me what it might be? So you go on the web these days, you know, Wikipedia, whatever. I put in climate 50 years, and it came up straight away with the Atlantic multi-decadal oscillation, an oscillation of 50 to 60 years. By the way, the other peaks are the fluctuations. They're at different frequencies. So there isn't only this one component, there are a lot of other components. And here is my estimate of the cycle. And you can see why I call it a quasi-cycle. Because this is a time-varying 50-year cycle. It isn't a complete sinusoid by any means. And it has kinks in it. But then if you're looking for perfect fit to anything in the climate data, well, you're not going to find it. But you are finding something that is a predominantly, on average, 50 years. And that's why it shows it. By the way, a peak in the spectrum that has shoulders is suggesting a time-varying mode. The way I was getting that, by the way, is called dynamic harmonic regression. Time-varying parameter harmonic regression analysis. That's available in Captain, very useful, and can be used for forecasting in its own right. All of the methods I'm using are optimal in stochastic terms. Okay? Right. Here's the model at the top, and I've broken it down so that you can see the CO2 forcing and the rest of the forecasting less the CO2. They both go through the same model, and I'm adding on the quasi-cyclic component that I've estimated, okay? So, Here then, on the left, is the component of the output due to the CO2. In the middle, the component due to all the other radiative forcing except the CO2. And on the right is putting them together, and you're seeing it against the data, but not accounting for the seasonal, the 50-year cycle. Now, if we account for the 50-year cycle, well, now we're getting fits of 0.979. It's explaining 97.9% of the real data. You can see that on the side. I've then corrected the data to remove the cycle. And now you see the fit, and that's what it's seeing underlying. That's the background that it had estimated originally, forgetting the cycle. Put the cycle in, and you then fit the data much better. Now, I would say that one of the problems when you send anything to a climate journal is they don't believe you can model these data to this accuracy. Okay? But if you're going to use this for forecasting, you've got to forecast the input. Now that is a difficult problem, because you saw what the series looked like. It's plotted at the beginning here. It's got these big jumps in it. You look at its spectrum, it's all over the place. You know, this isn't a series which on its own is easily modelable. But the DHR can get a model of it, and you can forecast it. But unfortunately, the uncertainty in the forecast grows pretty fast. Okay? But to start off with, say for 10, 20 years, not too bad. So if we're going to forecast for 10 to 20 years, which I would say is not bad, because it's nice to know 10 years ahead what's going to happen, then we can proceed with this. And just to show you that that's a stochastic analysis, dynamic model which is stochastic. And we look at what they do, the climate scientists. Well, they don't talk about uncertainty. That's a dirty word. They talk about scenarios. So these are the family of scenarios they look at. Now, in looking at those scenarios, they're admitting it's uncertain. But they don't want to say it's uncertainty. So these are the scenarios. Do you notice the expanse? It matches the uncertainty I'm getting out of the forecast of that. So they recognize that it's uncertain, but they don't want to say it's uncertain. Remarkable. Here's the forecast from the year 2000 to 2011, based on the data only up to 2000. And do you notice something? Did you hear about the pause in global warming, the levelling off of global warming, which occurred between 2000 and 2011? Yeah. And lo and behold, this model has forecast the levelling. Can anybody tell me why it levelled off, except those I've already told? Well, if one input, CO2, is going up all the time, and the 50-year cycle is going up and down, if the... It's going down. Yes, and at this point, and it's easy to forecast on it, it starts to go down, it compensates for the going up, and it stays level. Simples, as they say. An obvious thing. No climate scientist in 2000 forecast that would happen. I did this analysis in 2000, and I forecast it would happen. And the climate scientists don't want to know. You should see the comments I got from the climate scientist reviewers. I mean, if I was a sensitive person, which I'm not, I would have stopped doing anything, because I was an idiot. Oh, I've gone. Now, I made a little film from MATLAB. I've never done this before, so you must excuse it. I also was surprised that the resolution from MATLAB's pretty low. So you're going to see now a film of me forecasting every year 10 years ahead. And it's quite revealing, so you have to look quick, because I couldn't slow it down any more than this. Okay, so here we go, from about 1960. See, it's not doing bad, is it? Okay, then it's not doing so good. Oh, it's really gone bad there. Oh, but it's caught up. Why did it do that? Well, you can't forecast this quasi-cycle exactly, so you're going to get it wrong sometimes. It got it right in 2000, but it didn't get it right just before 2000. Okay. Right, now I've forecast from 2011. So this is my forecast of what's going to happen in 2011. And the first three, I did pretty well. But the next one, I'm down here and it's up there, right? But I have to say, this was a shock to the climate scientists as well, who were not expecting it to be up there. I would just point you back to other instances where outliers have occurred. So is this a real more rapid change, or is it an outlier? You can't say at this point. A few more years, then you can say. If it isn't an outlier, something's happening with the climate that has not happened before. If it is an outlier, it has happened before. So it's going to be interesting, isn't it, to look at the next few years. By the way, you can see I can't be wrong, can I? Because look at the uncertainty band. I've got it right in terms of the uncertainty, because I said it could be up there. And remember, I don't put this uncertainty on myself, the model puts it on. It's quantified from the data without my intervention. I'm not telling this model anything, except I have to make some judgment about order and things like that. And here, just to show you that if they'd only plotted the error against the multi-decadal, they would have seen straight away they're correlated. Not exactly, because we didn't expect that, but I think you can see by eye, can't you, that these two series, the error in the model, the first model that I got, and this index, can't be chance, can it? Now, what does it mean? I've estimated what it is, taken account of it. I believe it means there is something in the climate science models which is missing. It is the effect, some effect, a feedback effect probably, which is that the temperature of the sea is not being taken account of fully in forecasting the atmosphere. Now, I can take that input and build a model with that input in. And here you see it. I'm not going to go into this, but here's the Samo input, and I find a second order transfer function there, so I can bring this in. Here are the carbon emissions. I get the emissions. I can model the CO2 from the emissions quite well. So I can put that block in. This is the other forcing, not the CO2. That goes into the transfer function. And at the top is the coloured noise. And the coloured noise, when I've taken the cycle out, is a quite high order autoregression, suggesting there's still quite a lot of colour there. But it's fairly small variance. Now, this model is referred to in a report which you can download from my website. Not published, why? You know why. But it's got all of the details of this model and its use, for example, in automatic control. What would automatic control here be? Controlling the emissions to control the temperature. I haven't done that analysis. I'm retired, so I don't do everything I might want to. I'm working on robots at the moment, by the way, so you know, I'm working a long way from this so far. But here was an earlier study where I'm trying to control CO2. If I can control CO2 on the basis of this model, then I should be able to control the temperature. And in fact, you can see at the bottom that I was trying. This was a long time ago, certainly before 2000, I think. And you can see that the controller says reduce the emissions by that dotted line in the middle. You see, this was that was when I did it, around 2000. And you see it says you should reduce it that way, and in that sense the CO2 will carry on rising like that. See, there's a lot of inertia in this system, so it's going to carry on. But this is the temperature will level off at 2 degrees. That's what they wanted. That's what the climate scientists tell you they want. So you can use automatic control theory to design an emission strategy. By the way, they don't do this. They don't think of it this way at all. They try and infer what input would produce the output by working back through a differential equation model. Well, if you work back through a differential equation model, what do systems people say? Never do it. Why? Because you amplify noise as you work back. So what you get as your estimate of the input is a pretty poor estimate. You have to smooth it and do all sorts of things. Okay, well, that's what I was going to talk about, and just a few conclusions. The model is fully stochastic. I think that's important because surely this is a stochastic system. Surely it is an uncertain system. And it appears to match the climate scientists' perceived uncertainty if you look at those scenarios. It accepts the causation assumed by the climate scientists. So it comes to conclusions which are quite similar to the climate scientists for different reasons, as you've seen. Are there ideas of causation right? This has said they seem reasonable, but it hasn't proven anything. So we still have to, think about the fact that this model is representing what climate scientists think is happening, because they say the radiative forcing causes the rise, and there's some reasonable supposition on a physical basis for that. It's credible because when you break it up, the different time constants and sensitivity match what climate scientists would think is acceptable. It's a quick and non-exhaustive analysis. When you're retired, you don't do long, because you haven't got any research assistants. So you sit at your computer and get back trouble, which I've got at the moment, and I managed to stand here without having to sit down, which is remarkable. Perhaps I'm psyched up well.
Be careful with the step.
Yeah, that's right, yeah. But I say at the end, but shouldn't a more comprehensive, inductive and prejudice-free analysis of the same general type that emphasises the uncertainty be part of global warming studies? I believe it should. The climate scientists don't believe that. I think that is an indictment on the climate scientists. Thank you very much.
Thank you, Peter, for this interesting presentation. It was so interesting that I could listen to you, all day long.
Yeah.
It was very, very nice, very pleasant.
Peter, when you said that your uncertainty matches more or less the IPCC projection, well, we shouldn't read too much into that, because this is really apples and oranges, because your uncertainty is driven by the uncertainty on the structural behavior of the system, and their uncertainty is driven by different emission. That's why they call them scenario, isn't it?
It is indeed. Let me try and explain that. It's my interpretation, because I couldn't say. If we had a climate scientist here to answer that. My feeling is this, that in their scenarios that they choose, some of which you'll notice are that reducing, are a reflection of their uncertainty in their brain. Right? So they're saying, oh, well, it could be this, it could be this, it could be this. And that is their uncertainty. And it's just interesting that their uncertainty happens by coincidence to match the uncertainty that comes from the uncertainty in the data. It's a pure hypothesis.
I see. Clear. We always said that people massage the uncertainty till it gets to some point where they feel comfortable with that.
That's right.
I agree with you 100%. A second short question. Well, a short leveling off How short? Because if the cycle is 50 years and it's just about started, as your
Yes.
plot shows, it could be also go a couple of decades.
It could, and of course, how well you forecast depends on how well you forecast the cycle. And it's a quasi-cycle, so you're not going to forecast it exactly. You saw it didn't do quite well just before this. So the answer is it depends on the coincidence of the cycle, if it's a causative influence, I believe it is, and the rise caused by the CO2 in this particular case. And at any point, you can't really say what it's going to do. At 2000, they happen to coincide at a point which caused levelling off. But whether that levelling off will occur in the future, I would think it would sometime. But you can't guarantee it because you can't forecast the quasi-cycle more really than 50 years, obviously. But really, you should 20 years as much as I think you should do.
Thank you.
By the way, I emphasised my differences of opinion with the climate scientists. If there were any here, and I apologise, because you have to emphasise your differences to get the point over. My differences are perhaps not as great as I've been implying.
Thank you for your talk, for your more or less provocative talk. The people who are dealing with a model based on partial differential equations, they put a lot of physical laws inside. They use parameters you can more or less measure. Mm-hmm. And so they claim that their approach is better suited for forecasting, especially if you are dealing with scenarios which are different from the calibration period. So what about your approach? How can you apply your approach under different conditions?
Well, if I understand you correctly, the first thing is that the climate scientists don't say explicitly that they're doing things for forecasting. On the other hand, all of their output that gets to the media is about what's going to happen in the future. So I think that implicit in what they do is forecasting. And for me, the interesting thing, I do what is interesting to me. I don't have to satisfy any more university requirements for publication and other things like that. I do what interests me. To me, it was interesting to see how well I might be able to forecast the atmosphere. So that was my motivation. Their motivation is much more than that. Okay, they are interested in the mechanisms and all these other things and trying to explain things at a finer scale, local effects and things like that. So they do a lot more than I have done here. But one element of what they do is forecasting, in my opinion. Now, the second part of your question, could you repeat that, please?
Yes, it's what is the reliability of a forecast when you use something which is calibrated on data? It is quite good if what you are forecasting is close to the data.
Yes.
But if you move to some scenarios where you may have some different things appearing, like decrease of CO2 emissions,
yes, okay. But but remember how I said the objective is important. My objective was not doing what you say. If I was doing that, I would build a meta model, like you do this week. And I could then play tunes with this model. But I would have to believe the model. I think you would now, if you used a meta model of a client, would you believe it as much as before you heard my talk? I hope not. And I think that is one thing I might say this week, is that when you're using deterministic models built by experts, remember that those experts are doing a very good job, the best possible job they can do. But in the end, they have a model with many parameters that could not possibly be fitted to the data. And I'm not sure that the uncertainty is always taken into account sufficiently for that. So when you do the exercise you're talking about, it's a different exercise. I didn't have that objective. I would have built the meta model if I'd have wanted to do that. And that's why I said very early on, I'm not going to do the full emulation. Okay?
So,
yeah. Thanks for a very, very interesting presentation. I was just a sort of devil's advocate question. I just wonder, like, when you identify the sort of modes in the error,
yes.
Is there a sort of way that you know that, let's say, they're in some way statistically significant, because you've got like what look like kind of three cycles of the error? Yes. You know, what's the chance that is there by chance?
Yes. This is where the fact that it's a stochastic model helps, because the uncertainty in fitting that model is reflected in the uncertainty of its forecasts. And consequently, in as far as the data are telling me something, you can say that this is significant, okay? Because the uncertainty is smaller than the errors that you get without taking it into account. All right. So I think that I could argue that this cyclic effect is a significant one. And if you then say, well, have I tested it out? I think that the forecast from 2000 is perhaps a test, because if the cycle wasn't there, it wouldn't have got the leveling out.
Other questions or remarks? No? Okay.
I just need a clarification about the uncertainty. In the RCP scenarios, if I'm right, they assume a future scenario of emissions based on political decisions, etc.
Yes.
What is the uncertainty you consider in the prediction you do?
Yes, if I understand you correctly, looking into the future of what the emissions will be, for example, is anybody's guess, isn't it? Particularly now Trump has been elected in the United States, I would say anything is difficult to predict. And Brexit in Britain, you know, I mean, things are happening we would never have thought. I never thought in my lifetime these things would happen, never. And so I hate to predict the future further than 10 years ahead, and I'm a bit reticent to forecast 10 years ahead. But if you look then at the forcing that the climate scientists say is causing the warming, then all you can do is model it as well as you can, okay? Or you can say that the climate scientists will tell you what it will be in the future in some way. So you can take what they say, or you can try and forecast it yourself. I just tried to forecast it as well as I could myself, and you saw I couldn't forecast it very well. The uncertainty on the forecast was large. And as I said in answer to Andrea, that uncertainty seemed to be matched by their uncertainty in the scenarios that they use.
Yeah, so what assumption did you take for the future emissions?
I can't hear you very well, so could you just speak up a little?
What assumption did you take for the future emissions?
Yes.
In your model?
Yes. Well, I'm forecasting on the basis of the historic pattern. Sorry. I'm forecasting on the basis of the historic pattern up to now. I'm not taking into account what might happen in the future. As I said,
so
to tell...
Increase.
Yes, I mean, you notice that in the data it's suggesting it's going to heel over, that it's not going to carry on going up in the rate it is now. The data are telling you that. It's interesting, isn't it? That in the data where they're saying it's rising incessantly, well, the data don't tell you it's rising incessantly. They say it's a curve over.
But actually, you model the inputs,
yes,
the emissions of CO2, and also of and the output, right?
Yes.
Okay.
So over the historic period, I've fitted to the data, and then I forecast on the basis of the model based on the historic data. That is all I can do unless somebody tells me what's going to happen in the future. I am not prepared to do that. I don't know enough about the climate system to be able to make any conjectures in that regard. So the best I can do, I think it's the best anybody can do, tell you the truth, at this point in time, is to look at the pattern that's happened in the past and to project on the basis of that. Now, if the global agreements on emissions had any relevance to the future, that we could say, it is going to reduce, then my projection into the future would take that into account, and my projection would come down faster. It would heal over faster. But I have no belief at the moment. Perhaps I'm skeptical, but governments say they're going to do things, and they don't necessarily. I mean, Trump's come in now, he says he's not going to obey the climate agreements. So can we say what's going to happen in the future? I don't think so. But I would hope so, but I don't think so.
Yes. Thank you for this very nice talk. I agree that it's amazing that climate scientists do not use this type of models. It's very surprising, but it seems there is some sort of gain of interest in this type of approach.
Could you, I've noticed in the week it's very difficult for people to hear. I'll come over there and then I could...
I'm saying that it's amazing that the climate scientists don't use this type of approaches.
Yes.
But it seems that there is a gain of interest in this type of models. And I went recently through a paper in the annual reviews in control, and when people try to promote this type of approaches. Yes. And I wanted to have your point of view on one particular fact, where they might be, I mean, the climate scientists might be wrong, in the sense that they probably, I mean, there is an important issue about deciding what is an input to the system and what is a response of the system. Yes, and I went through a paper where they mentioned the mistake of considering, for instance, the El Nino phenomenon as an input to the system. So I would have liked to have your point of view.
A product of the system. Yes. Yes, I believe that my analysis points to work of the kind you're talking about. Effectively, I think that if the climate scientists take any notice of what I'm doing, what they would do is to start to look to see what in their models could create feedback connections, teleconnections, they even use the term teleconnections, that could give rise to this cycle being part of their models. And I think that's the way forward, personally, and I hope they go along that way. At the point that making this talk today, I haven't seen it, but you've obviously seen some signs of it, which is comforting, and you reported it. Thank you.
Maybe on that, just add a few words.
And what is your take on the solar cycle? Now they say that solar cycle number 25, it will be weak. You see anything of this periodicity in your data?
I didn't look for it specifically. You noticed there were a number of peaks in the error, and some of these could have been associated. I didn't personally look for it. My feeling, I mean, they take it into account in some way because the force, the radiative force, it includes something solar. So to what extent they took it into account, I have not researched that.
Okay, thank you, Peter, for your intervention.